Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lecture we were discussing classification and regression trees, and specifically we were talking about the data set on the promotional offers. We were looking at the variables of those data sets, and we identified the pin code particular variable which is going to be categorical variable, which is a categorical variable, and then too many categories, 96 of them we saw in the previous lecture, and we wanted to find out ways where we can actually reduce the number of categories to a fewer number, so that the dimensionality problem is solved there. So we generated a bar plot which you can see here, and we wanted to analyze this particular bar plot to understand whether some of the categories can be grouped together. So if we look at the this particular graphic, we can see that some of the bars having 0 values, right? Some of the pin codes, they have 0 values, so that therefore 0 offers have been accepted in those locations here and here. So of course when the task is to predict the class of this our outcome variable promotional offer, so with respect to that we can club these two locations in one group, because the level of acceptance or rejection in this in these two particular locations, 2 or 3 depending on, because this is quite a big plot. So all those locations which have similar acceptance level, we probably can group them. For example, other bars we can see, for example this one, first bar and the third bar, they also have the similar acceptance level 5, right? So probably we can group them. So we can also identify many other locations for this one, right? So many other bars which are at the similar acceptance level, and probably we can group them. We can also group them by having a different range, right? So we depending on the exercise and depending on the suitability of that particular grouping with respect to our model and its performance, we can start grouping. So for example, the pin codes with 0 to 5 acceptance count, probably we can group them, then 5 to let's say 8, group 2, then 8 to 12, group 3. So in this fashion also we can group group these locations. So we look at this particular scenario, then we'll end up with just 3 groups. However, what we are going to perform here in this our exercise is depending on the acceptance, whether it's 0 or 1 or 2, because we have only the maximum value is 12. So for each of the acceptance level we are going to create different groups. So as you can see, rather it's 13. Yes. So depending on the different different grouping strategy can be done. So we can also do this range based grouping. We can also do this. So this one seems less suitable, but in our exercise we are going to perform this, and this could be another grouping mechanism. But however we will have to justify, we will have to try and understand why this range and why this particular range. So we will have to understand probably these locations are having lower levels of acceptance, probably these locations are having medium level of acceptance of promotional offers, probably these locations having these acceptance numbers, they are having slightly higher in our data set, as per our data set, slightly higher level of acceptance. So in this fashion also we can perform grouping. However, for our exercise we would like to have so as you can understand, we started from 96 pin codes, right? So from 96 we can have this situation also 3 groups, and we can also have this one as well, where we end up with 13 groups. So for our exercise we are going to perform this one. However, this can also be done. So once this is understood, we will have to do few more computations, so that we are able to group all those records in appropriate category, new categories that we are going to create. So what we are going to do is the count of a pin code, the count that we have computed, right, the count of pin code, that we will treat as a label. So if a particular pin code has a 0 acceptance count, so that becomes its label 0. If the pin code has a particular pin code, so number of pin codes which have 1 acceptance count, so that would be their label 1. And if they have 5 or 10 or 12 acceptance count, so that is going to be the label. So all the locations depending on the acceptance counts that they have, so that is something that we are going to treat as the label of that particular location. This is mainly to simplify our coding and simplify our computation, so that we can easily group them. Later on, if we want, we can give them appropriate name. Instead of saying 1, 2, 3 or 13 or 0, we can also say group 0, group 1. So later on, that kind of transformation can be done, but for our purpose we will stick to 0, 1 and up to 13, these 13 labels, and we will later on convert it into a factor variable with 13 groups. So this particular loop, as you can see, so what we are trying to do here is assign count of pin code as its label. So pin codes having same count will have same label, and therefore that is how they will be grouped. So loop, you can see X in pin names. So for all the pin names, all the pin codes that are there, so loop will run for those many pin names for each of them. And first we try to compute the index where this particular X values they are same. So first we select all the records having the same pin code, and once those records, indices of those records is known using index variable, then pin code of those indices that is being assigned this number, which is nothing but the count of pin code, right, the acceptance count of for that particular pin code. You can see C pin code where we had the counts. We are trying to identify the pin code indices where the same pin code is there, and once it is known, the length of index that we already know, so that is going to be repeated. So C pin code count of all the locations, all the records where same the same pin name is appearing, same pin code is appearing. So for all those we are going to give that count. Rep is the function, so it is going to repeat. So this is going to be equal to the indices that we have already computed, right. So let's execute this particular code, and then we will be more clear. Once it is done, you would see that TF1 pin code. You can also look at the environment section as well, but if you compute this, you would see all the this particular variable different records that we had, 5,000 of them. So all the records in the pin code variable, now we have the count, right. So 7, 3, 4, 4, these counts actually represent the acceptance level of that particular location. So because if the count is same, so they are again in the same label, they can be easily grouped. So in this fashion we are trying to group them. Now once we convert this variable into a factor variable, so now if we again look at the values of this variable once it has been converted, so you can see labels, you can easily see 0 to 12. So 12 labels are there, and now this particular variable has been converted into a factor variable. So other variables that we wanted to transform into factor variables for education, so 3 labels we had, so let's convert it. The promotional offer also online. So let's look at the structure now, However, education was I think already it was factor, so we repeated the exercise. So in this fashion you can see now the promotional offer is factor variable appropriately mentioned here. The pin code, now you can see 13 levels, and so we drop down the dimensionality from 96 to 13. So one of them is going to be taken as the reference category. Now the education and online also 3 and 2 levels respectively. So now all the variables are in their desired variable type. Now we can go ahead and start with our partitioning exercise. So in this particular data set we have 5000 observations. Out of these 5000 observations, we will take the 50% of them, that is 2500 observations in the training partition. Out of the remaining 2500 observation, we will take first 1500 observation in the validation partition and the remaining 1000 observation in the test partition. So let's sample. So the partitioning is in this particular exercise slightly different, as you have been watching that in the previous other techniques, other lectures, when we did partitioning, we just created two partition, training and test partition. So there the training, the sample indices we computed using the sample function, randomly drawn indices, and that were the part of the training partition. The remaining indices, they were assigned to the test partition. Now if you look at this these 4-5 lines of code for partitioning, first we are trying to randomly draw 2500 observation from the sample for training partition. So let's do this. So you can see part index has been created in the environment section, the integer vector of 2500 observation. So now these observation can be safely assigned to the training partition. So this is done. Training partition is created with randomly drawn 2500 observations of all 9 variables. Now the second we again call sample function, and now in this case you would see that all the observations which are remaining, now you can see this vector, integer vector, and the remaining observation we do minus part idx. So the remaining observations, so remaining indices, now out of those indices we can again randomly draw 1500 further observations for our validation partition, right. So in this fashion, let's again create this index. Now because the way we have randomly drawn these indices, right, replacement is also set to false. So there is no overlapping observation in the training and the validation partition. If you want to check the same, you can check using intersect function. So intersect function will give us if there are any similar rows, similar values. So part idx and part idx1, if we run intersect function here, you would see we see no values. So these are two different set of indices. So now we can safely create our validation partition by selecting the 1500 randomly drawn indices and the remaining indices. So remaining ones which is the where we part idx and part idx1, both of them, once we remove them out, the remaining one are going to be the part of the test partition. So in this fashion we can actually do our partitioning. Now we come to the next part, that is once our partitions have been created, we can use the training partition to build our model. So if similar exercise that we did for the sedan car owners, that sedan cars data set. So here our outcome variable is, we are using rpart function, and within the rpart function the first argument is the formula. In the formula you can see promo offer is our outcome variable, and this is being modeled against all other variables which are predictors. Method is class for classification model. The data is appropriately mentioned as df1 train, the training partition. rpart control function, which we talked about in the previous lecture, to control a certain aspect of our tree model, right. Its complexity parameter is 0 because we want to grow full grown tree, and we minimum is split just 2 observations, minimum bucket 1 observation. So all these parameters we have already talked about. Xval is 0, so if we don't particularly specify this value 0, the default value is 10. So some observation is going to be used for cross validation by our part function, which we don't want to do. So we would like to use all the observations just for the training, building the model. And the validation, we have the validation partition for to perform the validation. So we don't want to make any we don't want to use any observation for this cross validation exercise, that is inbuilt in the R part function. So xval value has to be 0. Other parameters is split. This is the Gini metric that we have discussed in previous lectures. So let's execute this code and we'll build the model. So now mod 1 is created, as you can see in the environment section. Now let's look at the tree. So let's set the parameters, graphics parameters, margin, outer margin, and XPD. You can look at the parameter function, power function, for more detail. So this is basically XPD is basically to generate your plot in the device region. So you can, if you are interested in more detail, you can find out from the help section. Now once the graphics parameter are set, then we can generate the plot. So this is our basic plot. Let's add the information. Now you can see the plot is quite messy here. So this is what we were talking about. If we have very large data set and we generate a full grown tree, so it is going to be quite messy. So you can see the number of splits, too many splits are there, because as we talked about in the full grown tree, we also did the exercise where we were partitioning the observations right in the Sedan core data set, and we kept on partitioning till all the observations were classified correctly. So the same kind of thing happens in a full grown tree, where we continue to build our tree model till all the observations are classified, till all the partitions that we create are pure homogeneous partition. That means all the observations belong to the same class. So because of that, too many partitions, and the full grown tree is going to be quite big, as you can see here. If you want the nicer version or pretty version of this particular plot, so as we have been doing, as we have done previously, PRP is the function that can be used. The relevant package we have already talked about. So we can generate this, and you would see that this is the another way of representing this full grown tree. So this is slightly better version, but again, because the tree is quite big, so because of that this one also looks messy. But however, we can look at a few things. For example, first split is done using income variable, and this is value is 101.5, and then the if we can look at other splits, right, the spending and education, right, and then further spending here, income here, family size and income. So you can also see pin code, and you would see the different categories of pin codes. They have been used using commas. Had we used pin code as an ordinal variable, right, then we would have seen some numeric kind of value, right, because it would have been treated as because it already has too many categories, so we could have treated it as numeric variable, and then it would have some numeric value. Because we have treated its categorical variable, we can see specific categories as part of different subtrees. So we'll discuss more on this as we go along. So let's come back. So the sniping exercise that we had done with using the previous data set, something similar we will have to perform in this particular case, because this is quite a large tree, and the full grown tree is quite large in this case. So if we want to see just first 4 labels, so that we are able to understand what are the rules, what are the important variables, and how the split is happening, if we want to visualize that. So first 4 labels, how we can go about this. So first we need to do the node numbering, as we talked about in the previous data set. So you can see node numbering has been done. So all the nodes have been numbered now, 1 2 3 starting 4 5. So because this tree is quite large, so you can see most of the node numbers visible in this case, right? The earlier some of the numbers were missing, but now you would see 1 2 3 is all the initial node numbers are there, right, up to 13 14 15. So quite in a sequence many node numbers can be seen here. Let's using these node numbers we can always snip off the tree part that we are not interested. So toss was one of the argument, the second argument that we use in the snip r part function, as you can see here in this particular line. So we need to compute this, so we need to create this particular argument, right, variable, the number of actual node numbers which we want to snip off. So let's first create task1. So this is the function mod1 and the frame. So we talked about r_part.object, and one of the element there, one of the attribute was frame. So within frame we also have row names. Row names will actually have these node numbers. So more detail you can always find using the r part, this particular, you can see r part object. You can see, look at this page in the help section, you can see frame. So for any r part object there is going to be a frame attribute which will be actually a data frame with one row for each node in the tree, and the row dot names of frame contain the unique node numbers that follow a binary ordering indexed by node depth. So these are the node numbers that we actually shown in the tree. The same node numbers are stored in this particular attribute frame. So from this row dot names we are trying to extract that information, and then those names, then we are trying to convert it into integer variable. So let's compute this task1. So you can see task1 having 109. Since we have 109 total nodes, the tree, the full grown tree that we had built, it has 109 nodes. So for all those nodes, the node numbers, the unique node numbers that are assigned by the algorithm, so that has been captured. So once these numbers have been captured, we can sort them. So all this we are doing so that we are able to identify the nodes which we want to snip off. So once we sort, so these numbers might not be in order. So if you want to have a look at this, you would see that 1 2 4 8 16 17, then suddenly 34. So this numbering is slightly the way this is recorded in row names is slightly different, right? You can see 1 2 and 4 8. So you can see the row names, they are recorded in this fashion, 1 2 4 8, and then 16 17, then 34 68, right? So in this fashion these row numbers are recorded. So this is slightly different. So therefore we will have to sort this out. So let's create another variable with sorted values. So once these values have been sorted, we would like to identify the nodes which we want to get rid of. So how we can do this? So let's again zoom into the full grown tree and with node numbers. So for example, first 4 labels, so label 1 2 and 3 and 4. So after these 4 labels we would like to get rid of the remaining part of the tree. That means the nodes is starting from node number 16. So let's go back to the code. You can see the same thing I have mentioned here. So toss2, this is so 16 and up to the last node, right, length of the toss2. So from the node number starting at 16 to the last node, I would like to get rid of these nodes so that we just see the first 4 labels. So let's compute this. So this is done. Now as you can see, I am using snip.r part function here. So mod1, and we would like to snip it using the toss3 argument containing the nodes to get rid of. So this is done. Now we can use prp function to print the tree. Now you would see just 4 labels of the tree. Now this is quite clear, easy to understand what is going on here. So you can see first split is income less than 101.5, and then we have splits at using spending, and the split using education at the right part, the left part spending, then further spending, income, family size, income. So these are some of the common variables. You would see income and spending, they remain the two important variables here. Income is spending, family size is also there, and the pin code is also visible here in this part. You can see pin code is also there. So income, spending, education, family size, pin code are the important variables. However, the income and spending seems to be occurring more often. So now since the whole full grown tree is developed, to understand more about this full tree, we can look at few more things. For example, number of decision nodes that are there. So again, R part object, this particular split attribute that is there, it will give us the, so splits contains the information about the variables used for split. So we can also length of this particular attribute will give us the number of decision nodes. So 54 decision nodes have been used, and we look at the terminal nodes. So total number of nodes would be can we find out by the this frame. As we looked at the help section, that frame contains a unique row number for each of the nodes. So therefore it can give us the total number of nodes that are there. You can see 109, which we already know, and then once we subtract the number of decision nodes, we will get the number of terminal nodes 55. So as you can see, number of decision nodes 54 and number of terminal nodes 55, which is much more one more than the number of decision nodes. This is property of binary trees. In binary trees, the number of terminal nodes or number of leaves are one more than the decision nodes. Now if we are interested in having a table where we have the information about the variables which have been used for splitting and the split values, so the predictor value combination, if we want to look at that list, so by default the output that we get out of summary function, it is more descriptive, right? So we would like to have a tabular output, then we would have to write the code for the same. So here we are essentially trying to do this. So we are trying to capture the split variable information and split value information. So particularly split value for each of the split variable, because as we saw that in R part object, split function has the information on the variables used for split. So for all those variables, can we extract the split values from the model. So let's compute the split values. So split value, let's compute. So we have two counter. J is the counter for split variable, I is counter for split values. So then split value is the this variable where we are going to record all the split values. So let's initialize this one and also the counters. Then in the loop you can see X in mod 1 frame var. So for all the variables that are there, so frame has all the information on all the variables. So we run a loop for all the variables, and then we place a check there if as dot character and leaf. So if the particular variable is the leaf node, right, if the particular that variable is leaf node, then we would like to skip that. If it's not leaf node, we will like to continue. If it's if it's a leaf node, we would like to skip and go to the else part. So within this we see that if the variable is not factor, right, so there the split variable could be factor or numeric. So again we do a check. If the split variable is not factor, that means numeric variable, then simply the value of that split value can be find out using this particular code, where the splits attribute that we discussed and the index column that is there, the index particular column is actually contains the split value, and J is anyway counter for split variable. So for that split variable, and index column will have the split value will be immediately recorded or captured here. If we go to the else part, which will essentially deal with the factor variable, so here if we go to this part, we have another variable CL as null initialized. So split, if the split variable is factor, so k is another counter that we are starting, which is ranging from 1 to largest number of labels in the factors. So the different factor variables that we have, the pin code had the largest number of categories, right. So it had 13 categories. So k will be lie between 1 and 13. We are running a loop for the those number of categories. So you can see k in 1 to a number of columns that are there, and CS is split. This is particular attribute actually contains information about factor variables, so it will have that information, and once it has that information, so we can run the loop here, and within this we can look at again we are getting this temp variable where we are recording this information of index. So this index and particular label, so for a particular variable and its label, so there are going to be different categories for a factor variable. So we get further information. That information would be whether the label of that particular variable is going to be recorded in temp. So if that goes into the left child, so for a particular factor variable or categorical variable, if it has 4 categories, so once the tree is being constructed and the categorical variable is the split variable, we have to check which category is going to the left side and which categories are going to the right side, right, whether A is going here and B, C, D are going to the right side. So the same information, the same thing is being captured here in this code. So once we have recorded whether a particular label, right, that is represented by k, right. So k is running for all the labels, right, maximum of labels, therefore it will run for all the it can be used for all the variables and all the labels. So if it is goes for left, goes into that particular label goes to the left child, left branch, then that is being recorded here, right, that is being recorded in CL, that CL variable that we had created class. So this we are recording here, and then you can see the next line here in the else part itself. Again for all the labels, so this loop will run, and for all the labels we would end up recording this, we would end up recording all the labels, right. So those labels are actually nothing but the values, specific values for the categorical variables, right, just like numeric variable, the specific value which was used for split. So these labels, different labels, which label has gone to the left part, which label has gone to the right part, they actually represent the split value. So you can see split value, that variable that we had initialized. So numerical variables are being stored in the if part, and in the else part we are storing the categorical variable. So here we will keep on storing using this particular function, using this particular code, we will keep on storing the value for categorical. Now the second else part that we have, the else section that we have, so this was for the leaf node. So if we come and arrive at a leaf node, then we assign a split value as NA, because leaf node is not the decision node and it will not have any split value, and then we continue with our counter. So this is the code. So this is how we can go about capturing, extracting the split values. So we will continue our discussion. We will stop here. We will continue our discussion in the next lecture from the same point. Thank you.